Welcome to APCTP string seminar. It's great pleasure to introduce today's speaker, Takashi Tsuda. He is a PhD student in YITP, and recently he published an interesting paper on the orbifold CFT with Professor Tadashi Takayanagi. And today he will tell us about this paper for the free fermion cyclic symmetric orbifold CFT and its calculations for the entanglement entropy. Please join me in welcoming our speaker, Tadashi.
Thank you for introduction. I firstly thank to organizer that inviting this seminar. Yes, my name is Takashi Tsuda, and I will talk about this topic. Yeah, this is based on the joint work with my advisor Tadashi Takayanagi. Okay. Today, I will talk about general features of cyclic orbifold CFTs and symmetric orbifold CFTs in the first half, and the latter half, we proceed to some examples like calculations in Dirac fermion or orbifold CFTs. Okay. In the first half, I briefly introduce such orbifold CFTs, and I will discuss the torus partition function, and I show some connection between cyclic orbifold CFTs and symmetric orbifold CFTs. Okay. So what is symmetric orbifold CFT? The definition is as follows. We prepare some two-dimensional CFT. We call this CFT as seed CFT. And we prepare the n times tensor product of seed CFT C with n copy of seed CFT, and orbifold the n times tensor product by using the symmetric group Sn, and we get the nth symmetric orbifold CFT. We can also get nth cyclic orbifold CFT by orbifolding by the cyclic group Zn in the same manner. This is the definition. And why symmetric orbifold CFTs are important is this slide. Okay. One point is some specific symmetric orbifold CFT is very similar to D1, D5 CFT. In other words, D1, D5 CFT can be regarded as some deformation of specific symmetric orbifold CFT. Yeah, this is the D1, D5 setup, but this is not so important. Okay. Okay. The conclusion is that D1, D5 CFT can be regarded as the deformation of T4 SCFT of the symmetric orbifold CFT of T4 SCFT or K3 CFT or something like compactified. It depends on the compactified manifold. But this is the one important point. Okay. And the second point, not specific symmetric orbifold CFT, but general, it's this is a general features that symmetrical for CFTs are something similar to two-dimensional holographic CFTs. This theory has a large central charge when we take large n limits. If we take the central charge of seed CFT as C, then we get NC central charge. And also, in the large n limit, the theory has sparse low energy spectrum. And also, some operators in symmetrical for CFT exhibit large n factorization, and these three conditions are necessary conditions for holographic CFT. And yeah, but I should notice that symmetrical for CFT is not the exact holographic CFT, but something similar to holographic CFTs. For example, symmetrical for CFTs in the large n limits represents phase transition at hagedron temperature, regardless of the choice of seed CFT. And this is the same property of to the holographic CFT. And this phase transition is from their sparse low energy spectrum and large central charge. Okay.
Some simple question.
Okay.
What is the role of sparse low energy spectrum in the previous page for holography, the existence of holography?
Okay. Okay. Holographic, for example, holographic CFT has sparse low energy spectrum means that classical operators have very sparse means that not so many states in around the vacuum because they have only matters that we know scalars or gravitons or something.
Yes.
And in the case of symmetrical for CFT, the symmetrical for CFT has also a sparse low energy spectrum that is enough to show phase transition.
Let me ask in this way: to have some thermal behavior, we to have some thermal behavior, for example, black hole, then we need some dense spectrum at least at high energies.
Yes.
Yeah.
They have dense high energy spectrum. Yes.
So I don't. So this seems to be some opposite. I mean, that's the reason why I asked. I mean, for ADS sparse low energy spectrum, so what is it necessary for sparse low energy spectrum for ADS geometry? Well, I do not have any understanding.
Yes. Below the threshold of black hole energy, the general ADS CFT case, in general ADS CFT case, the theory has sparse sparse spectrum below the black hole threshold.
I see. Let me consider it more. Thank you. Yeah.
Okay. Thank you for asking. Okay. And okay. So symmetrical for CFT has no interaction because if we choose free CFT as seed CFT, and thus we can solve in principle. So this means that symmetrical orbifold CFT is a good toy model for studying holographic CFT. And there's some recent progresses like application to ADSB CFT to research on boundary states in symmetrical orbifold CFT, and marginal deformation, and to construct a new family of holographic CFTs that starting from n equals 2 super minimal models, they get some maybe new family of holographic CFTs that can be constructed. Yeah, yes, that they maybe found that new family of holographic CFTs like this. So this is the second point, second important point of symmetric orbifold CFTs. Okay, now let's move on to the discussion on torus partition function. Okay, the torus partition function of symmetric orbifold CFT, we write Z sub ns can be written in terms of the seed partition function Z and the Hecke operator T, like this. This is the famous results in here, like, and this Ni runs partitions of N like this, and this T denotes a Hecke operator. The definition is this. Okay. So we have to introduce Hecke operators because this is not famous in physical field. So this operator is used in mainly context of number theory in mathematics. So okay, Hecke operators map modular functions into other modular functions, and this is the definition. And we want to check some example. For the case I is a prime number, P. In this case, this D runs the divisors of P. That is a 1 and P, and the action of Hecke operators on Z becomes to like this. This term is from D is one case, and this summation is from D is P case. And for the next non-trivial example case, like I is equal to 4 case, this D runs over 1, 2, and 4, and these are corresponding terms. Okay, this is the brief introduction of Hecke operators. And an important feature is that Hecke operators keep modular invariance. If we start from modular invariant function Z, TIZ is also modular invariant. Okay, and yes, by using the Hecke operators T, we can write down the symmetric orbifold CFT partition function like this. Okay, and now we want to check that this partition function is admits the ordinary orbifold CFT consideration, like we know that orbifold CFT partition function can be decomposed as like this.
예, 말씀하세요.
전화 괜찮으세요?
지금
여보세요?
Okay, okay.
Yeah, go ahead. Sorry. Yeah.
So this
sorry for interruption. Sorry.
okay, 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 no problem. And this box denotes G twisted sector partition function with insertion of H in time direction like this. And we can interpret this representation as this box description. Let's see the NH2 case.
So for the symmetric and also the cyclic, both are same formula or probably different?
I haven't talked about cyclic orbifold case yet. Okay, okay. Thank you for asking. Yes, this is the yes. We check the N is2 symmetric orbifold case. The partition of N runs over 2, 0 and 0, 1, and this summation comes into like these two terms, and we know that this T2Z is equal to these terms, and we get this we finally get this representation, and this description matches well to the box representation, like they're corresponding like this. Okay, okay. Yeah, here I should notice that this NH2 case, the symmetric group is the same as cyclic group. So this is also the partition function of second cyclic orbifold CFT, but this is this is this is I have to tell you that this is also the Z2 partition function. Okay, okay. We can check that N is more larger than 2 case, but there is a time limit, so I will omit. Okay, okay. Then I have to introduce the connection to cyclic orbifold CFT. And we can see the connection through Heck operators. Here, symmetric group Sn is a little bit complicated. So we want to start from more simple group, like cyclic group Zn. And we know that every element in Sn can be decomposed into product of cyclic permutation. So it is natural notion that we expect that there is some specific relation between symmetric orbifold CFT and cyclic orbifold CFT. And there actually is such relation. And we find the method to write down the cyclic orbifold CFT torus partition function by using Heck operators. And this method enables us to analyze the structure of twisted sector in symmetric orbifold CFTs by considering the corresponding cyclic orbifold theory. Okay, so we have to so Okay, the partition function of cyclic orbifold CFT can be written as the sum of the deformation of Hecke operators like this, and phi is a Euler function, and this TSF is a some deformation of Hecke operator T defined as the linear combination of normal Hecke operators, and for I without some square factor, Ti and Ti, the deformation of Ti is the same operator, and we call this deformation of Hecke operator as square-free Hecke operator, because I said that because this is the reason we call square-free. Okay, so now we check the examples of square-free Hecke operators. For okay,
This is also modular invariant, like a square factor.
Yes. This square-free Hecke operator keeps modular invariance, and
Both S and T, right? Like S information and T.
Yes.
Okay.
Yes. That's right. And yes, we have to check the normal Hecke operator T4 has 4 terms, not 4, 7 terms like this, and this term is equal to normal partition function zeta, and this is modular invariant itself. So and the square-free Hecke operator eliminates such modular invariant parts, and we define this like this, eliminating this part. This is the example for the I4 case, but this square-free Hecke operator is defined to be minimally modular invariant part of Ti for all I. For example, if we take T12, this includes, for example, a T3 like this, and we have to consider the square-free of 12, and this is defined to be like this. And the proof of the construction of cyclic orbifold CFT partition function is omitted in this seminar. See the detail in our paper. Okay, but okay. Yes.
So is there a orbifold, or is there a way to construct theories which directly gives this square-free thing as the partition function?
Your question is that the ADS CFT case.
Do these TSFs correspond to the partition function of any kind of particular orbifolding? Right?
No, because we have to sum over the TSF to get the full partition function. So this itself does not the partition function of some CFT. For example, this has not integer coefficients of Q. Q means the e to pi I tau. So we have to sum up some TSF to get some partition function. So is it okay for your question?
Yeah, thank you.
Okay, thank you for question. So we can calculate quantity in symmetric orbifold CFT through cyclic orbifold CFT, where the calculation is relatively easy. If we are interested in some TI sector of symmetric orbifold CFT, what we have to do is to consider the ith cyclic orbifold CFT. We will see some examples in the latter half of this seminar. Okay, so this is the end of first half. So if there is any questions, please do not hesitate to ask. Okay, so let's move on to the part 2.
So question. So
okay.
Let me try to understand this part. So any symmetric orbifold can be recasted in terms of GN orbifold. Is this the claim?
Yes. Yes.
But so although I think you showed many things, so sorry, I think I did. So how is it possible? So sorry for this.
Oh, okay.
Yeah.
We have to take closer look at this construction, and we have to pick up some TI contribution from this summation. So yes, we have to yes, this procedure is a little bit non-trivial. So I will not explain the sorry that I had not explained the detail, but yeah, the procedure is a little bit non-trivial. Yes, we have to pick up some only TISF contribution and sum up to reconstruct the TI.
So how the TI operator can mimic symmetry orbifolding or any symmetry orbifolding?
This TI?
Yeah, either TI or TISF or whatever. Yeah, scale free.
Oh yes, yes. This is the known result that the symmetric orbifold CFT can be decomposed as the sum of the product of some TIs. And yes, we have to study on each twisted sector in so symmetric orbifold CFT, and then by yes, looking at these twisted sectors can be done by using cyclic orbifold CFT technique. This is our claim.
Okay, let me consider it more. Thank you.
Okay. Sorry that maybe my answer is not enough, but thank you for asking.
And I have another question. So
Okay.
I remember this kind of people also studied some orbifold CFT between the cyclic and the symmetric. There is some other between them, like I forgot the name, but is there also for those orbifold is there also way to construct the partition function in this way, like some scalar vector?
So let me ask again that what orbifold CFT?
I forgot. Like here you consider this permutation group.
Yes,
Sn,
yes.
and then you also consider the Zn, which is
Yes.
the cyclic group. There is a lot of group between the permutation and the cyclic. Like a cyclic is basically like abelian, but there is some group which between which is bigger than Zn, but the
okay.
there is some word for that, the orbifold, some orbifold.
Okay. Very interesting question. I think there is some description by using such Heike operators, but I think that the group that is bigger than Z but smaller than S have no series that is depends on n, like, so there's there are only a finite case that is between the n and Sn. So and we what we want to calculate is the large n case. So yes, that case is actually not in our interest, but thank you for asking.
Okay, thank you.
What is phi I by d again?
This phi is Euler function that counts the phi n counts the number of co-prime number that yes, this phi counts the integer that is less than n, and co-prime number that's to co-prime to n. So like if we take prime number p, then this is p minus 1, or the case 3, this is trivial. 4 case, this is
Thanks,
2.
got it. Yeah.
Okay.
Thank you. So is it clear that once you sum up TSF, though TSF itself, like you said, do not have integer coefficients and so on, if you sum it up with this phi I by d, like, is it easy to say that the sum ends up having integer coefficients? Is it very clear?
Your question is why this coefficients appears?
Yeah, is it obvious that, like, if you sum up TSF with this weight, they should give you always integer coefficients, like it's a valid partition function at the end?
Okay. You say that this construction gives actually the integer coefficients. Okay. And that is yes. But
is there an easy way to say why is it?
Okay, easy way. Okay. So
No, it's okay if it's like a longer
yeah.
manipulation.
So sorry that I can't explain in short. So if you are interested in the detail, let's talk later, or you can see the paper. Thank you for asking. Okay, and now let's move on to the calculations in Dirac fermion orbifold CFTs. Firstly, we'll talk about the replica methods in ordinary Dirac fermion, normal Dirac fermion in two-dimensional CFT, in two-dimensional CFT, and we move on to cyclic orbifold case, and we discuss some extensions to symmetric orbifold CFT, and this is a interesting point. I will talk about the periodicity and connection to holography in symmetric orbifold CFT.
I have also question. So previous discussion,
Yes.
is about the partition function and so on. It does not matter whether it's a fermionic CFT or not, or
so
probably it doesn't
yeah,
matter.
there will be no problem because we start from modular invariant partition function, and so but yes, in this case we focus on the NS sector of fermion, so I think there is no problem, but maybe there is that I have not noticed, but yes, I think there is no problem.
Here you are only consider NS sector or Ramon sector? Like,
only NS sector.
I see. Okay.
Okay. So I will review the replica methods in ordinary Dirac fermion for shortly. The nth Renyi entropy for the subsystem A on some Riemann surface is like defined like this, and the rho A is the density matrix on the subsystem A, and taking the n is to one limit, we can get the entanglement entropy on the subsystem A, interval A, like this. So what we are interested in is this quantity, trace A of rho A to the n. And this can be calculated by inserting replica twist operators on the at the endpoint of the interval. And these operators create branch cut that 2-pi rotation around the insertion point reaches to the next replica sheets, like this. And for the Dirac fermion case, the operators turn around the endpoint like this. The psi changes as like this. Psi goes to from one seat to the next seat, and so we perform the discrete Fourier transformation. We can translate the change of sheets to the getting the phase factor around when turn around the replica twist operators. And so we want to find some operator that gives the such phase factor change. We can get by bosonizing the fermion, and the twist operator can be written as written by using the bosonized the boson like this, and we can check that the OPE holes like this, and this part gives the phase factor when the z turns around the z1. Okay. So what we have to do is to calculate the calculate the correlation functions of the twist operators like this, and this is proportional to z1 minus z2 to the p square over n square on the plane CFT. And the results combining with anti-holomorphic sector is the L to the 1/6 times n minus 1/n. Like yes, we set the size of the interval L, and this leads to the nth Renyi entropy like this. And especially we take if we take the n to one limit, we get the entanglement entropy on the plane in the famous formula like this.
So here, this is also like only for with the. I mean, it doesn't matter whether it's Dirac fermion or not, or like a. It's generally applicable for the any CFT or.
Yes, the replica method is a very general method, but we can formulate like we can write down the explicit form of twist operator like this is the only Dirac fermion case. Or something like more very simple CFT case.
I see.
Yes, but yes, this method is very general. But yes, yes, okay.
So when you say Dirac fermion, is it free Dirac fermion?
Yes, yes. So we consider the two-dimensional Dirac fermion. So yes, this is the two-dimensional case. Okay. Thank you for asking. So we consider the case on the torus with complex structure tau. And here we focus on the NS sector. Okay. And the results of the trace over rho to the n is like this. And this leads to the nth Renyi entropy like this. And the first term corresponds to the universal term, like this is locally this is log L. And yes, and the second term is very non-trivial contributions. Okay. And we expect Renyi entropy on the size of interval L on the torus to satisfy this equation. This is the Renyi entropy on the some subsystem A, and this is the complement entropy on the complement of A. like this, and the difference of these quantity will be of the form like this. By we can we expect that this quantity can be written in terms of partial function. And this is geometrically natural guess because the replica method suits each torus along the interval A. So if we take the interval A as the whole space-like direction, and or if we take the interval A as the point in the spatial direction, the difference will be the n tau over the z to the n, like of log of them, like this. And we can check this is correct for the Dirac fermion case. Yes, the results is like this, and here the ZNS denotes the NS sector partial function, and we use the theta function identity like this. This is like n-tuple angle formula, and we can combine the summation over this to like this. Okay. So now we move on to the
Question in the one
Okay.
more. So what is the interpretation of second term?
second term,
Yeah.
this one. Yeah, this is from the this is so physical interpretation. That okay. So yes, we consider the CFT on the torus. So there must be a non-trivial contribution from the something like non-local yes, non-local correlation. So yeah, this is the case for every two-dimensional CFT or on the torus. Yes.
Can you have this quantity from holographic calculation? For example, if we consider some another geometry calculation, is there any result? Yeah.
I think there is a second term contribution if we consider like holographic CFT on torus, but I'm not sure about the detail of the holographic case.
Thank you.
Thank you for asking.
I have one more question. So what about if you consider the only NS sector, then what about this modular invariance? Or here maybe you don't need this modular invariance. So
yes, we do not consider some modular invariance. Yes, we forget the structure of modular invariance here.
I have another question. Maybe I think maybe it's trivial, but
yes,
in general, you can consider here you say orbifold, but
yes.
Here is it cyclic or symmetric orbifold? Or like in general, you can write down this partition function of is it like here this orbifold is like you maybe write down this orbifold partition function of the cyclic or symmetric, and then if you take n goes to one limit, do they give the same answer? Probably. That's all.
So
Maybe this is some wrong question, possibly wrong question, but I may misunderstood this like a procedure, but here you talk about this orbifold to calculate the entanglement entropy, right?
yes.
So usually I think it's a cyclic orbifold, right? This is it.
This calculation is on the normal Dirac fermion.
Dirac fermion of the cyclic orbifold.
No. This is normal one. The case of n is one case.
Okay.
Yeah, this is the review of the calculations of normal Dirac fermion case.
Yeah. Okay.
Okay. Thank you for asking. Yes. Then we move on to the cyclic orbifold case. Yeah. So this is a very complicated point that there are n fields on the torus. Because we take n times tensor product of the fermion, and in each twisted sector, the fields get changed. Operators get changed when turning along the torus. Like if we go turn along the torus in the spatial direction. For L prime sector, the operator changes like this, and if we go along the imaginary time direction, the operator changes like this, and on the torus, the n sector partition function of the cyclic orbifold CFT is of the form like this. And yes, we can see that this partition function is splitted into the sum over the twisted sectors like this. Okay. And we extend the previous procedure to nth cyclic orbifold CFT case. We have to perform the discrete Fourier transformation for twice. Like this, and finally we bosonizing the fermion and constructing the replica twist operators as we have done in the normal case. And here we have to I have to say that this psi has two okay, this psi is labeled by two figures that k starts from 0 and ends in n-1, and p is from -n-1 over 2 to n-1 over 2. And yes, we should distinguish that this capital N and small n, like for cyclic group Zn corresponds to the capital N, and nth Renyi entropy, n is lowercase n. So, and corresponding to this fact, the psi has two figures on like this. Two characters. So yes. Okay, and okay. And we can calculate the entropy, Renyi entropy on the in the LL prime sector like this, and the universal part is very similar to the previous case, but this is n-folded because we take n times tensor product of the seed theory, and yes, second term is of the form. Okay, and we can get the entanglement entropy for LL prime sector by taking n to 1 limit, like this. But yes, this is the very we need to get this quantity by using very technical calculation. But we want to see the full Renyi entropy on the torus. Yeah, we want to calculate the entropy that includes all LL prime sector, and it naively seems to be sufficient that we simply add up the all LL prime sector like this. However, this construction is not sufficient. For instance, thermal Renyi entropy is not take the form like this log z n tau over z tau to the n. This is because that different twist boundary conditions are allowed on each replica seat, and this contribution we call off-diagonal contribution is missing to this construction. Okay, now what happens in the let's see now what happens in the n capital N and lowercase n is 2 case. This is 2 torus that is denotes the different replica sheets. And on this torus, we set twist boundary conditions as L1 and L1 prime, and we can set another different boundary condition to the second replica sheets like L2 and L2 prime. And if we take different twist boundary condition, the operators are related to each other, and we cannot formulate the replica method calculations to 2-point functions, but yeah, this non-trivial relation. Because of this non-trivial relation, that the 2-point function of replica twist operator to becomes to 4-point function of scalars like this. Yes, and we succeeded to evaluate the such non-trivial relations between the Fourier transformed bosonized operators and in n equals to 2 case. And the result is like this. This is very technical result. We can calculate the diagonal parts like as we done in the ordinary fermion, but we have to include the off-diagonal parts like these ones. And this sorry, that this second Renyi entropy satisfies the relation that is what we expected to the thermal Renyi entropy. Okay. So we move on to other quantity, like time like separated 2-point function. We calculated some specific 2-point function, and we find that this 2-point function has a real-time periodicity of almost n. And for other case, we consider the Z2 Dirac fermion cyclic orbifold CFT on the cylinder, and its second Renyi entropy has doubled real-time periodicity compared to the normal Dirac fermion case, like this. Normal Dirac fermion cyclic orbifold has normal Dirac fermion on the cylinder has periodicity of like this length, and Z2 cyclic orbifold case we have the doubled periodicity. So we can conclude that n cyclic orbifold CFT seems to have real-time periodicity. And okay, and so we want to discuss the extension to symmetric orbifold CFT. Okay, and we can calculate the diagonal parts of the Renyi entropy for symmetric orbifold CFTs by using the method that I told in the first half of my of this talk. Still, it is hard to obtain the full Renyi entropy because there's an off-diagonal contribution. This is one of the future problem of this research. Yes, okay, and we can also formulate calculations of some correlation functions in symmetric orbifold CFTs. We think that this can be done, but we have not tried yet. And this is some some interesting results. I think we can read off the periodicity of symmetric orbifold CFTs by looking at the relation between relation to cyclic orbifold CFT. Okay. This is the form of diagonal part of thermal Renyi entropy on symmetric orbifold CFT. And yeah, this is very complicated, but yes. like this, and so now I talk about the periodicity and relation to holography. We can read off the periodicity of symmetrical for CFTs. Since nth symmetrical for CFT includes Ti for all I that is from 1 to n, and each Ti sector has periodicity I from the results of cyclic theory. The symmetrical for CFT has periodicity of least common multiple of from 1 to n. And this is exponential n growth in the larger limits. This is the famous result in number theory, like this. The vertical line shows the log of LCM, and the horizontal line denotes n. And we can see that the log LCM is almost the same as y is equal to x minus 2 pi. And this is consistent to the Poincare recurrence time of BTZ black hole, like this one. Yeah, this is heuristic discussions, but this is I think this is something interesting. Okay. Oh, this is the end of the latter half, and I want to summarize this talk.
When you say periodicity, you mean periodicity in 2-point functions, right?
Yes, partially yes, but yeah, yes, yes, but if sorry, that if we consider the if we consider the Renyi entropy on cylinder, we can see that the periodicity is also doubled or n-tupled. So this is the
this periodicity is in the length of the interval, or like is it some temporal periodicity? What do you mean by periodicity for the entropy?
This periodicity means that the periodicity of the theory we think. So that yes, the definition
the
of
periodicity in n, is it? Or what? I'm sorry, I'm not able to understand what is periodicity of entropy.
Okay. You say that this part. Okay. We can consider the real-time evolution of the interval. So if we take this is so sorry, and this is okay. Okay. The entropy has entropy is defined on the interval, and is like this, and so sorry that okay. Okay, we have to consider the entropy on the cylinder. We have to set the coordinate as like this, and the entropy has entropy is a function of the size of length of the interval, and the time direction, imaginary time direction, like this. Here we consider the real-time periodicity, so we move the this interval to the real-time direction, and we catch the periodicity of the Renyi entropy. So sorry that my English skill. Is it okay for your question? Yeah.
So do you mean yeah, I still really didn't get it, because it's a okay,
Yes.
so it's a periodicity in tau, is it? No, or something like, maybe I didn't understand what you said.
Tau.
No, periodicity in like what periodicity? You place the interval at some point, and then what is the periodicity appearing in? Like,
in this case, the periodicity is of the periodicity of the entropy, and in terms of the
maybe
real time
formula. If in the formula, if you tell me what variable has periodicity, maybe then I'll understand. Right.
Sorry that I can't catch your question.
It's in the formula, right? This is the formula for the if in the formula for the Renyi entropy, like if you tell me what variable has periodicity, I will follow. Like
sorry
periodicity
that
in which variable, like
which variable? Yes, if when we consider the cylinder, we have imaginary time direction, and the entropy has the where the has the variables of where the entropy the subsystem is defined in the imaginary time direction, and we see the real-time evolution of the imaginary time by using the analytic continuation.
okay. Thank you.
So thank you for asking. Okay.
So can I just confirm this? Like, so this is all at the level of like so there is a periodicity in the 2-point function of the Dirac of the fermions. Then there's a periodicity in the entropy, which is maybe the periodicity in the 2-point function of district operators.
Yes. Yes.
So like you also mentioned the Poincare recurrence time, right? So like so recurrence time only depends on 2-point functions, is it? Or like should I expect the same periodicity for higher point functions also? Like
we think that there are yes, we think that this periodicity holds for higher point function case. We expect that also the higher point function has the same periodicity, and Yes, so we consider this is the periodicity of the theory.
Okay, thanks.
Thank you for asking. Okay, let me summarize this talk. In the first half, we found a method to write down the partition function of the cyclic orbifold CFT on the torus with respect to Hecke operator Ti. And this reveals the relation between cyclic orbifold CFT and symmetric orbifold CFT. And the latter half, we considered replica methods in Dirac fermion cyclic orbifold CFTs. And here we find that we need to include off-diagonal contributions for full calculations of Renyi entropy. And we succeeded to calculate the n. N is capital N and lowercase n is 2Ks. And by using the relation between cyclic and symmetric orbifold CFT, we found the periodicity of the Dirac fermion symmetrical CFT has LCM from 1 to n, which is exponential n at large n. And some for concluding, we showed some future problems. We want to consider full replica methods in general n and n case. And we want to extend the result to symmetric orbifolds. This is, yes, a very important future problems. And we can extend the entropy calculations to the case with other CFT case, like T4S CFT, to study more D1, D5 like situation. And investigating black holes by focusing on the heavy operators that contribute to the long periodicity in symmetrical for CFT is something interesting, I think. Okay, and this is the end of this talk. Thank you for a long time.
Yeah, thank you very much for the nice talk.
Thank you.
And please ask question. For now, I have one question.
Okay.
Here you consider the NS sector.
Yes.
In the Raman sector or scalar field, you have zero mode. So if there is some zero mode, is there some like some special treatment or some other like first like is it this old method is applicable to this zero mode, like when you consider cyclic or symmetric orbifold, zero mode is like straightforward, or do you need some special treatment?
Zero mode. Okay. Okay, zero modes. Okay. What we okay. I think that we can calculate the as the same to if we yes, I think we can calculate if we include all the sector like our sector in the Dirac fermion case, but I'm not sure about the free scalar case, so I'm not sure that if we consider the case of the scalar field.
Okay.
Thank you for asking questions.
I apologize, but I know you explained this many times, but could you remind me when you said you have to consider off-diagonal terms?
Off-diagonal means...
What did you really mean? Yeah, what it really meant?
Okay, off-diagonal means that we can set different boundary conditions, different cyclic twist boundary conditions for different replica sheets.
So what does it mean? Like as you go from one sheet to next sheet, the periodicity changes across each sheet, or?
Yes. If the operators on this sheet turns along the for example, like space direction, the fields changes to J plus L1 in this sheet. But we can formulate in this sheet we can set different boundary conditions like this.
I see. And then but when you wrote down this formula for partition function using Hecke operators and all, like all this kind of choices didn't affect that? Wasn't that?
Yes.
Because I thought that formalism, I assumed every sheet is okay. This is one for replica. Okay, this is for the replica sheets, not the symmetric.
Yes. Sorry that yes. This is a very complicated point of this research. So
okay.
Yes.
Yeah, thanks. So one thing I want to ask is like there is so except for this this is what you mean by off diagonal. Is it like if you change the periodicity across sheets, you have to include such contributions? Like what do you exactly mean by off diagonal here? Like why is this why does this correspond to an off diagonal contribution?
So okay. This off diagonal contributions is needed to admit the form of thermal Renyi entropy like this. And yes, the thermal Renyi entropy has of the form like this is we consider the something like consistency conditions for the correct Renyi entropy, and we have to include off diagonal parts to we have to include the off diagonal parts to satisfy the Renyi entropy to satisfy we need to include the off diagonal parts that because Renyi entropy must satisfy this condition. Sorry, that's my skill. My English is very terrible. Sorry. We need to realize this condition for Renyi entropy on torus, and yes, then this requirement this requires us to include the off diagonal parts.
I see. Okay, so and I want to ask one more thing. Like, is there like a Hecke-like operator which can act on the Renyi entropies of the seed CFT and directly give the Renyi entropies of the symmetric CFTs? Is that a thing? So they're at the level of Renyi entropies, like, because this answer you had, okay, this is for single, okay. Yeah, so like directly the Renyi entropies, is there something you can just do to the seed CFT Renyi entropies to get the answers to the symmetric CFT?
You say that can we you say that your question is that can we get the orbifold CFT entropy by performing Hecke operators on the seed CFT entropy?
Something like Hecke, yeah, like.
I think that is very so yeah, maybe there is some kind of operators like satisfying that property, but yes, but I think that this is not the Hecke operator, like, because but
I guess the confusing part is this off diagonal things you mentioned, because as you have to go from, if you change the periodicities in each sheet and so on, like, or maybe not, because the apart from the off diagonal part, I thought you showed this formula where it was just log z n tau by z tau power n, and right?
Okay. So
yeah, this the previous
this is the diagonal part of the entropy.
Right. At least this part, maybe there should be something simpler, right? Like,
yes. Okay. And so yes, the diagonal part is related to. I think the diagonal part can be understood from something like Hecke operator like methods. But yes, the off diagonal part is very difficult to understand from like such Hecke operator like way. Okay. Yes. So. Yes.
okay, thank you.
Okay. I'm sorry that. Okay. Thank you for asking.
Okay. Is there any other question?
Sorry, I have a question.
Okay.
So you found that the periodicity of the Dirac free fermion symmetric orbifold CFT is exponential.
Yes.
So do you expect that this exponential behavior is universal in any CFTs like programmatic CFT?
Yes, we expect that the symmetrical CFT with any kind of seed CFT has the same structure. Like yes, yes, I think that this may be the results for yes, universal results. Okay, universal results.
So you mean that any symmetric orbifold CFTs has a behavior like BTG, even though free CFT?
Yes, but this is not so surprising, because we already know that symmetrical CFTs have the phase transition at Hagedorn temperature in the larger limits. Yes.
Okay. Thank you.
Thank you for asking.
So is there any other question? If not, let's thank the speaker again.